Okay, so first let's complete our proof. Now, if you remember the problem that we were studying, where on Friday we had an explicit example, we will assume that we have some Hamiltonian, which will have some, let's say, initial, and we will assume that there is a potential which changes with time. There is this time-dependent potential term. And we will assume that f of at t equal to 0, this is equal to 0. And f at t is equal to some later on time t. We are changing our system, and we will assume that it is a slow change, and this f is 1. So there is this potential term, which initially it is turned off, and so we slowly turn it on, and at the time t, it is now fully included. So this will be kind of the system that we will be studying. And hf, we will call hi plus v. So we slowly turn on the potential. And the thing that we would like to prove is that let's assume that we have some state at t is equal to 0. This is in psi and I, where this psi and I is an energy of the ith state, energy of the initial Hamiltonian with psi and I is equal to E and I, psi and I. If this is satisfied, and if the interaction is turned on sufficiently slowly, then we want to prove that psi at t is equal to large T is equal to psi and f, where it is still an eigenstate of our Hamiltonian. At this time our Hamiltonian is hf, and this psi and f is equal to E and f psi and f. So what we would like to prove is that this psi at the time t is equal to t, the probability amplitude that it will be in some other state m, this is equal to 0 if m is not equal to n and, well, something else, non-zero if m is equal to n. So this is what we would like to prove. If we start with the nth state of our Hamiltonian at t equal to 0, when we make this change slowly, it will still be in the nth state. Of course, the energy of this nth state will be different, the wave function of this state will be different, but nevertheless, it will still be in that state. Now, we need two quantities over here. One is this one, psi m of f. And if v is sufficiently small, then we can use the time-independent perturbation theory. And if you remember, in the time-independent perturbation theory, this is nothing but psi m, the initial state, plus the corrections. The corrections are the sum over all other states of v km divided by ek minus em. These are all energies of the initial Hamiltonian. And k. And of course here we also have f of t, which is nothing but 1. So this is the eigenstates at the later time t. Now we need this psi at t. This is what we need. Now if you remember, we can always write this as c, let's say L Cm psi m e to power minus I Em I of t, no, EMI times t divided by h bar. Since it's these psi m's, these are all I of the initial Hamiltonian, psi m's are a complete set. We can always write it in this form, and this will be, these coefficients will be time dependent. That exponential will be the exponential if there was no perturbation. And so we can solve for Cm of t, and if you remember our solution for Cm of t, we had defined this matrix of C's, C at the time t was equal to the time-ordered exponential of minus I h prime I at t prime dt prime from 0 to t, this matrix acting on C at 0. That's what we had obtained in time-dependent perturbation theory. And up to first order in interaction, this was nothing but 1 minus I over h bar, sorry. From 0 to t, h prime of I t prime dt prime acting on C of 0. Capital T, what we are assuming is we have our Hamiltonian. Let's say we have a particle in a box. That was one of the examples we studied. And the box, it has this size initially. We slowly move the wall of the box, so it just moves, and finally we come to this point at the time t, and it stops. So there are parameters in the Hamiltonian which change slowly over time between t equal to 0 and t equal to large T. That's the final time. But of course, they can keep changing. I mean, there is nothing in this calculation that assumes that at the time large T it stops. But we look at the problem at time t equal to 0, where we have the initial Hamiltonian, and then we look at the problem at the time large T. And we would like to show that between these two times, no transition happens to other states. So what this tells me that the Cn at the time t will be nothing but 1 minus I over h bar Vn. If you also remember what the definition of h prime I is, h prime I was e to the power I over h bar h0 of t, h prime e to the power minus I over h bar h0 of t. This was the definition. This can also add a time dependence. And if you just take the and the evolution of the nth term, now this is the matrix, not just the time derivatives in this example, because we are already looking in a particular basis. These are the expansion coefficient in that basis. So h prime I, every operator should be expressed as a matrix, and this is the corresponding matrix. And if you write the corresponding matrix for this one, for the nth term, because initially we assume that the Cn is non-zero, all the other ones are 0. So Cnn receives this 1 minus I over h bar Vnn, the integral from 0 up to, now let's look at large t, e to the power I over h bar. Well, there's no e to the power I over h bar, because we are looking at the nn matrix element of this one, and from the left-hand side we get e to the power I over h bar En of t. From the right-hand side we get e to the power minus I over h bar En of t, and they just give 0. So here we end up having f of t prime dt prime plus higher order terms. This is for Cn. Now for the other terms, Cm at t, well, at t equal to 0, Cm was 0. So there is no contribution from this 1. And the other contribution is minus I over h bar Vmn 0 to, let's look at the time t, e to the power I over h bar Em minus En of t prime, f of t prime. And now that's it. This is for m is different from n. Now let's look at this one. This will be the one that we are actually interested in, because this is what causes transitions from n to the other states. But also keep in mind that these cause transitions from the nth state of the initial Hamiltonian to the mth state of the initial Hamiltonian. So we don't want these to be 0. They need not be 0. because the final eigenstate, the eigenstate of the final Hamiltonian expressed in terms of the eigenstates of the initial Hamiltonian will contain many states, not just the nth one, because they are eigenstates of different Hamiltonian. But let's look at this term. Now we are looking at the adiabatic condition in which f, well, it can be 1, which is not small, so we cannot neglect f, but we know. Now we know that the time derivative of f is small. So we might first try to write this as a time derivative of involving something, involving the time derivative of f. So that's the trick we will be doing. So then we can say that, okay, that time derivative is small, so ignore it, and then we can continue. Now to do that, this is Vmn from 0 to t. Now, we want to do the adiabatic approximation, which means that the time derivative of f is small compared to some other parameter, or some other time scale in the problem. So that is what we are looking for, that we don't know f can be large, but we know that f prime is small. So we can ignore f prime. Well, here it doesn't appear. It's in the integral. But we can get it out of the integral, f, by doing an integration by parts. If we do an integration by part, the integral will contain the derivative of f, which we can ignore. So that will be the trick. But to do the integration by part, we have to have some derivative somewhere. But I can do this one. I over h bar em minus en of t prime is nothing but, if I take its derivative, this is h bar over I 1 over em minus en. So if I take the derivative of the exponent, it will cancel those factors that I inserted. F of t prime, dt prime. Now these h bars cancel, this I will cancel. Cm at the time t will be minus Vmn. Now if we do the integration by parts, this is e to the power I over h bar em minus en of t prime 1 over em minus en f of t prime. Evaluate that t prime is equal to 0 up to t prime is equal to t, minus from 0 to t e to the power I over h bar em minus en of t prime 1 over em minus en df by dt prime. Now this is the term that we will neglect. And in the first one, just keep in mind that f of t is equal to 1 and f of 0 is equal to 0. That's how we define that. We assume that we are turning on the potential very, very slowly. At t equal to 0, there is no potential. At t equal to capital T, we have the full potential. Now, of course, for this approximation to be true, now the condition for adiabaticity is that the second term should be small compared to the first one. That will be the condition. Now, we will come back to that point, what that means later on. So let's just continue. Cm of t is equal to minus Vmn e to the power I over h bar em minus en of t prime over em minus en capital T. Now basically that's it. So this is our Cm. Now we can write down our full state. Psi at the time capital T is, let's see, this is the coefficient of the nth state. f0 is 0. 1 minus I over h bar Vn and the integral from 0 to t of f of t prime dt prime. So it is this term. This is our Cn of t. This is multiplying psi n. E. And then we have this minus. Of course, here we also have e to the power minus I over h bar En of t. Now why? Because if you look at our expansion that we started with, we have these exponential factors over here. So they are already factored out, so I have to include them now when I'm writing the full state. Minus Vmn There will be a summation. M is different than n. Well, I think I made a sign mistake somewhere. Probably this is minus, this is plus. So this is all here are minuses. And so here I have a minus Vmn. Then I have 1 over Em minus En. E to the power minus I over h bar Em of t. So this should be the term that I should have. Well, here, if you look at above, there's also this En term. So this is no, hold on, no, there's no minus sign. Now let me just keep Em minus En. Now this is plus, but this one gets multiplied by e to the power minus I over h bar Em of t. So what is left is still e to the power minus I over h bar En of t. And psi m. The two exponents are the same. Now let's also get the other one. We had this one. And this f of t is just 1. Now we need to take the inner product of the two. Psi of t, psi m, f. This is equal to, well, the inner product of the first term just gives me the first terms in both of them. 1 minus I over h bar v and n from 0 to t, f of t prime, dt prime, Kronecker delta mn. This is the term we want. Then let's continue. We have the first term times the second term in the second expansion. In the first, we take this one and this one. No, it's not necessarily 0. Now, you see, it will give me Vmn 1 over Em minus En, e to the power minus I over h bar En of t, This is there if m is different than n. So you see, there I have a sum of terms which do not contain the n. And when I multiply it with psi m of I, I'm basically projecting out the mth term. Okay? So if I project out the mth term, what remains is whatever that factor we have, Vmn times 1 over Em minus En, blah, blah. But of course, the mth term exists in the sum only if m is different than n. If m is equal to n, then this term is 0. And then we have a similar sum with this term over here and the first term in the expansion of the time-dependent wave function. Well, let's see, plus okay, this and this one will give me the k is equal to n term Vnm divided by En minus Em so what I have this one multiplying this term over here. Well, I would just say 1 because the other one will be second order. And e to the power minus I over h bar En of t. If I have, for example, this term, multiply with this one, or that term multiply with this one, that is second order in V. Yes. Plus terms, of course, I will have plus terms of the order of V squared. Now, apparently I have, of course, here I also have 1 minus Kronecker delta Mn, and it seems that I have made a sign mistake. The first one. Well, that is this, yes. E to the power minus I over h bar En of t. The third term. Well, I would rather have that one, this one. Yes, I want that to be minus. Let's see, you mean here in integration by parts? So here I have minus makes a plus. So this one you are saying is a plus sign. Well, let's see. Here this is minus Vm and this is multiplying everything, but no, that's a minus sign. This term, I mean, the second term here, that's just 0. I'm ignoring that because f prime is 0. Where?
So if you go to the step before that, before this one, you took the derivative, you should have a minus now. Because the exponential is minus, when you take the derivative, you have a minus.
No, I said that's a plus. Yeah. That's a plus. Now, probably I made a mistake in this expansion. Probably this was not Ek minus Em, but Em minus Ek. Anyway, if you go over the calculations, paying attention to the signs, what happens is these two terms, they just cancel each other. That is the basic truth. So if they cancel, what you end up having is this matrix element this is equal to something multiplied with Kronecker delta Mn. Plus, there are corrections of the order of V squared. This is basically the trick. Now, ordinarily, since we are doing perturbation theory, we are assuming that V is small. So that corrections, in general, one would expect it to be of the order of V, not V squared. So it tells me that it is really small. If the adiabatic condition holds, the correction is really much smaller than the first order correction. And indeed, we had only calculated the first order terms, not the second order terms. Everything is correct up to V squared. And in fact, we can even prove that there are not even corrections at the order of V squared. Now, that is what we will prove now. So let's assume that now what happens if V is not small? But nevertheless, we just turn it on slowly. So basically what we will need to do is we start from H0, Hi, let's say at time t is equal to 0. We turn on the interaction slowly, and this becomes H, let's say 1 at t is equal to t over n, which becomes H2 at time t is equal to 2t over n, which becomes H3 at the time t is equal to 3t over n, and which becomes Hf at t is equal to large T. So instead of going from Hi to Hf in a single step, we can just assume that we take several steps from Hi to Hf. And H1, Hi, let's say, no, Hn is equal to Hn minus 1 plus V over n. We are just turning it on slowly. At every step, we increase the potential by V over n. So at the end of the first step, and this n is arbitrary. Arbitrary as long as V over n is small, that we can use perturbation theory, so we can use our previous result. N is large, but arbitrary. So the transition probability Evet. Yes. At every step, the change in the Hamiltonian can be treated as a perturbation. Now, that is what we had done in the previous step. We just said that, okay, there is our Hamiltonian changes slowly, and the total change in the Hamiltonian we can treat as a perturbation. That is what we had assumed in the previous step. Now, what I am saying that is, let's say that we cannot, let's consider a case we cannot treat the change in the Hamiltonian as a perturbation. In that case, I can still consider very small changes added together. Each change can be treated as a perturbation. So eventually I add up all the perturbations. Now at every step, my transition probability, therefore this is m is not equal to n. the transition probability to a different state will be equal to V over N squared. That is what we had shown over here. Corrections to this one are of the order of V squared. And since we are taking N steps, at the end the probability of a transition, well, will be typically multiplied by N, which goes to 0. So although in the previous derivation we assumed that the change in the Hamiltonian is small, now this argument shows that even if the change in the Hamiltonian is large, these corrections that are, we said that there can be of the order of V squared are in fact 0. So as long as we have the adiabatic approximation, these terms over here are actually 0. Not just of the order of V squared. We only proved it up to the order of V squared in this step. But in this next step, this is kind of the general proof. That even those, the corrections of the order of V squared, they go to 0. Hmm?
Why is the name scheduled as we said? There is no energy input even though we change it. And why it's called adiabatic?
Why is, like in thermodynamics, okay, so let's see, in thermodynamics the name adiabatic comes from there is no heat. Well, you see, there is no heat given to the system. Well, you see, heat, there are various ways of generating the heat. It doesn't have to come from, it usually comes from outside, but for example, if you, let's say, you are in a room, isolated room, you yourself, and you shout. You are breaking a diabetes. It's no longer a diabetic. It's not reversible. You cannot reverse your shout. Hmm? So, you are creating entropy. Or you just move your hand like this. It's no longer a diabetic because you created kind of a shock wave. You can move your hand backwards, but nevertheless it will not be the same thing. You are not it's not reversible. Only if you move your hand very slowly, in that case, you can say that that's a diabetic. You are in an isolated room. No, the whole system is my system. If you make rapid move. Yeah. Well, you are kind of generating heat due to chemical reactions. Yeah, you are generating. But you are creating heat, you are increasing the entropy of the system. You are generating heat, nevertheless. You see, suppose you are burning. You are converting chemical energy into heat energy. That's probably where the name derives from. Now let's go back to our adiabaticity assumption. You see, if we can neglect the second term compared in this line, if this integral, this one, if this is much smaller than the first term, let's say everything is at large T, this is our adiabaticity assumption in absolute value. So let's look at the first term, the integral. This integral is less than the absolute value of the integrand, the maximum value of the absolute value of the integrand, 1 over em minus en times df over dt, the maximum value, times t. This is a typical estimate of that integral. So this should be, if this is much, much less than the absolute value of the right-hand side, f of t divided by em minus en, then we are happy. If this condition is satisfied, then we can do the adiabatic approximation. Or df by dt maximum should be much less than f of t by t. This one, which one? If this is satisfied.
How can this be satisfied?
Well, how can this be satisfied? That's a good question. Can this be satisfied? You see, we have this function f of t. Well, this is at least, if this is satisfied, then we definitely have the adiabatic condition. Well, what this means is, let's say f of t is, this is the maximum value. It can be such a function. It starts from 0, it goes up to 1. Now, f of t over t is this one. The derivative of this one. So the tangent should be much less than the tangent of this straight line at everywhere, which is not satisfied. So this is not a good approximation. Now, you see, this condition is sufficient, but not necessarily necessary. Now, what are the other conditions that we can say under which this equation is satisfied?
Can we do the same thing, but we are only interested with the first part, for example? Say that we are increasing f from 0 to 2 tau, but we are only looking at the first part.
What do you mean the first part? The first term over here. So,
we can divide it into n steps.
okay, so what? So at each step, we are defining this f. Now, at each step, we define this f that goes from 0 to 1. The change in the v can be very small. It can be v over n, but at every step, f goes from 0 to 1. Now, let's do another thing. Okay, so under which conditions we can say that, I mean, your book just claims that, okay, this is satisfied is if df over dt is small. Okay, fine, but what are the conditions for this one to be small? Now we will take large t to be large. Well, basically I will say that t should be large. Okay, that should be one thing. T should be large because if t is large, then you see the first exponent, it oscillates. So if it oscillates, there will be cancellations. If there are cancellations, then I mean, this turned out to be a too strong constraint, and we cannot satisfy. I mean, it's true, if it is satisfied, then things will work. But I mean, for this inequality to hold, this might be too strong. Okay, you see, what we are looking for is under which conditions the inequality over here is satisfied, because that is our adiabaticity approximation effect. If this is satisfied, then all our derivations are correct. Now the question is, under which condition does this approximation hold? So that is the question we are looking for. Now what we want is, in fact, this just kind of gave us an idea in the sense that, okay, if we can approximate the integral by the absolute value of the integral by the absolute value of the integrand multiplied by the width of the integrand, then this is not satisfied. So this limit, this upper bound on the integral, on the absolute value of the integral, kind of has to be too big. Now if that upper bound is too big, it basically means that in the integral we need to have some cancellations. In the integral, if we want to have some cancellations in the integral, before taking the absolute value, kind of the integral should oscillate fast, so that there will be cancellations. That means t should be large. Well, how large? T times em minus en should be much larger than 1. Hmm?
1 pi or 2 pi.
Remember, okay, so this is one condition, at least t should be large. If t is large, then f prime is small. F prime is typically 1 over t, or f over t. Hmm? Well, you see, f will be a general function. So since it will be a general function, I mean, there's no reason why just one period should be enough. And you can have functions f such that one period might be enough. I mean, you can pick up some special function f that will be satisfied. But in general, f will start from 0. I mean, you see, this large t is also kind of arbitrary. Something we inserted it over here. Our function starts from 0. It can just rise so very fast, and then stay at the time t for a long time. So the derivative will be 0 for a long time, but for a very short amount of time, the derivative will be large. So that is not also something we want. So we want f to change kind of continuously and to increase from 0 to 1 at the end of our period. So the derivative of f prime is typically 1 over t. And since f prime is 1 over t, this condition basically means that f prime should be smaller than em minus en over h bar. No, sorry, h bar over. So if t is em minus en over f prime is basically much larger than 1, or f prime h bar. Right? Yes, over h bar. Or f prime should be much larger than em minus en over h bar. Well, I inserted the h bar just to make things consistent dimensionally. So f prime is the time derivative, so it's, yeah, okay. So here I have a h bar, because the exponent is em minus en times t over h bar. Now, this is basically the condition that we had also derived previously in our particular example. You see, em minus en over h bar is kind of a time scale related with our problem. It's the oscillation frequency of my wave. And f prime is kind of the changing inverse time. The inverse of the time over which f changes significantly. So we basically have two time scales. One is the time scale of the changes in the wave function. The other one is the time scale for the changes in my f. And what I want is the time scale of the changes in my f should be much larger than the time scale of in which my wave function changes. So until my f changes significantly, my wave function should be oscillating many times.
Can we interpret the integral as a Fourier transform?
Which one? This one. Well, in the Fourier,
Yeah, it's not from different.
I mean, I wouldn't, well, now there's the exponential oscillating sine and cosine. So if you want to call it a Fourier transform, maybe. But I think it will be just pushing too much. This, well, what I'm saying is, let's say f is a function something like this. And this condition tells me that the maximum of the derivative of f should be much less than the value of f at the time t, which is 1 by, at the time t, f is 1 divided by t. Okay, this is the condition that we want. Now, f of t over t is the derivative of this, is the slope of this line. Right? So you see, at this point, for example, the slope of my curve is larger than ft over t. So in fact, the f by dt at its maximum value would be equal to ft over t only if f is just a linear function. Otherwise, the maximum will be always larger than f of t over t. At some points it will be larger, at other points it will be smaller.
What if you divide this function into smaller functions?
Well, you see, it doesn't work because in our derivation, in many places, we use the fact that f is 1 at the end of our period. Redefine one. Yeah, okay, of course we can do it, but probably there will be other modifications in the calculation. So if it is not 1, just redefine v rather than redefining f. So if f of large capital T is not, let's say it is 1 over 2, I can just redefine v to be v over 2 and redefine f so that at the time capital T it is just 1. So if something doesn't work in this case, it won't work even if we divide it into smaller parts. And you see, even if you take this one, divide it into small parts, so that it won't have the value 1 at that point. Oh, okay, I can just do the same argument for this part over here, and nothing would change. Because the problem with this approach, this approximation, this condition is that you have this function f, which starts from 0, and it can go to, let's say, some other value. I don't really need it to be 1. You have a function that starts from 0 and goes to some other value. And the derivative within this limit, the maximum value of the derivative within this range, I want it to be less than the slope of this curve. Well, it just means that at least at a certain point it will go below this line, and once it goes below that dashed line, it cannot go up if that condition is satisfied. So you can never reach that final point. Because if you go below that line for a moment, even for one instant, if you want to go to that point, that final point, you have to climb faster. That means the derivative will be larger than the slope of the dashed line. So that's the problem. That condition cannot be satisfied, except for f being a linear function, in which case we have an equality. Yeah. I mean, if equality would satisfy us, then fine. We could just say that, okay, if f is linear, then we are done. But what we want is, we want this condition. This is what we are looking for. And we are looking for the conditions under which this will be satisfied. Now that will be satisfied, you see, f is changing slowly, so its second derivative will also be changing slowly, typically. If its derivatives are changing slowly, and if we have an exponent over there, if the exponent is changing fast, so df by dt, it has one value at an instant, at the next instant it will still have the same value, but the exponent would change its sign. So we get cancellations. So this condition would be satisfied if we have some cancellations. And to get that cancellations, we need the exponent to be large, at least for a reasonable range of the integration region. And we can get that cancellations if the exponent is large, that is, if this condition is satisfied. But basically that condition means that this condition is satisfied. Which means that within a time that my f changes significantly, my wave function should oscillate very fast. So basically that also means that since my wave function is oscillating very fast, in a single oscillation of my wave function, my potential doesn't really change. And to very small changes in the potential, my wave function just adjusts itself to that very small change. Now let's give a short break now, and in the next hour we can just analyze another exactly solvable problem. And see that the calculated transition probability, and we will see that the transition probability is not 0, but very small. And it goes to 0 in the limit that the adiabatic assumption is satisfied. You see, if f prime is very, very smaller than em minus en over h bar, the probability of getting to an alternative state becomes very, very small. So the better this condition is satisfied, the smaller the transition probability gets. But it's not actually exactly 0. It will be exactly 0 if f prime over that number goes to 0.